Living in Florida, we are all probably fairly familiar with a beach. But a beach is a shoreline. It's the boundary between land and ocean. And this is a dynamic interface. It's constantly changing. So in this video, we're going to look at how waves affect our shoreline. When we're at the beach, or the shoreline, which is the actual scientific term, we're looking at a transition zone, or a boundary between our oceans and our continents. But here we call this an interface, because an interface is where we have different parts interacting. So in addition to it just being where water meets land, we also have our gaseous atmosphere, which is interacting with both the continent and the ocean. And we see very different types of geology between our continents and oceans, as well as different forms of life as well. But at these interfaces, we generally see that they change very, very rapidly. And if you've ever sat at the beach and just watched an individual grain of sand move around, a single wave can move it completely out of your eyesight. So we see that the waves along our shorelines are very dynamic. They change very quickly and they affect this boundary. We see that there are a lot of different things that can change our shorelines. Here we're looking at an image where it looks like it's probably a hotel or a condo that's right along a cliff. This shoreline's been modified by waves and storms moving through, and eventually enough of this cliff is going to be removed that the entire building is going to collapse into the sea. But we're also seeing that sea level can also impact our shorelines. In places like Louisiana, where it's very low elevation above sea level, we're very quickly losing those shorelines entirely as sea level increases and covers the land. But we also have to think about our streams, where they're coming through and eroding and depositing sediment, as well as glaciers and volcanoes and all of our plate tectonics. But one of the most important things that we need to mention is human activity. We're going to see that humans have had a huge influence on changing our shorelines, and usually not for the better. And one of the reasons why it's not for the better is because humans love to build along our shorelines. If you've been to the beach, you probably noticed that some of the most expensive houses and hotels are right along the shoreline. But the issue here is, again, sea level rise and storms and human activity. Because we're now putting buildings along our shoreline, we can see that waves can instantly destroy our buildings. And when we have major storms like a hurricane, those waves can be incredibly destructive. What we're looking at in this image is a house built along the shoreline that was destroyed in a single day due to Hurricane Sandy. If this house had been farther away from the shoreline when it had been built, there's a good chance it would have been damaged significantly less than this figure shows. So ocean waves are actually going to be yet another interface. It's going to be a boundary between our ocean water and the gaseous atmosphere directly above it. And with our waves, this is just moving energy from one area to another by moving the water. And remember that our surface oceans move entirely due to the wind. So ocean waves get all of their energy and their direction of motion from the wind. If the wind is blowing super fast, our waves are going to move fast. If the wind is blowing to the northeast, our waves are going to move to the northeast. But we also need to be able to describe our wave and give it different characteristics. Some of these you might be familiar with and other might be new terms. But the wave height is just going to be the difference between the very top and the very bottom of the wave. And here in earth science, we call the top of the wave a crest and the bottom of the wave our trough. But in addition to just how tall or how high is the wave, we want to know how long the wave is as well. And this is called the wavelength. And we can measure the wavelength in two ways, either from crest to crest, from the highest to the highest region of two waves, or from trough to trough of two waves. So, depending on how tall the wave is and how long it is, this will determine the wave period. Just how much time does it take for an entire wave to pass? Generally, we see that waves are moving through in a matter of seconds. The wave height, the wave length, and the wave period are all going to depend on the wind speed. We're going to see that faster wind speeds will lead to higher wave heights, shorter wave lengths, and shorter wave periods. But it also depends on how far the wind blows. So wind isn't continuous. It can blow maybe for 10 feet and then stop. And it also depends on the amount of time that the wind blows. The main thing from these last few slides is to remember that the surface water of our oceans is totally dependent on the wind. If the wind starts flowing, the ocean water is going to flow in that same direction and at close to the same speed. Waves move in what's called a circular orbital motion. If you've ever been in the ocean and played around in the waves, if you stay in one location, the waves are going to push you up, and then they're going to push you back down. You'll be at the surface of the water the entire time, but like we see with this boat, it's going to look like it's being moved up and down in the water, even though it's staying in the same location. And this is because waves actually move in a circular pattern. One thing you might have noticed so far throughout the semester is how often we're seeing these circular patterns around our planet. It helps cycle things and keep them in moderation. When we look at our waves, though, they're going to be very different in deep water versus our surf zone, where our waves are breaking and you might actually see surfers. So in our deep ocean, because the water column is so deep, we see that the waves are very, very short. If you've ever been like deep sea fishing or on a cruise, generally as long as the weather is fair, there's not going to be crazy up and down motion in our deep oceans. But the closer you get to shore, you're going to see that your waves seem to be making you move up and down even faster along our surf zone. As our waves are moving from deep water into our surf zone, the seafloor beneath it is getting closer and closer to the surface. So this is going to affect how deep the waves can be, but it's also going to affect the speed in which the waves can move. In deep water areas, we're going to see that the waves moving faster because it's not touching solid rock along the seafloor. But when we start moving inland and into our surf zone, because the seafloor is getting closer to the surface, it's going to slow those waves down. And because the wave's moving faster farther offshore than it is near shore, we're going to see that the waves get taller and taller as they get closer to the beach. But the waves can only support a certain weight of water. When the wave gets too tall, it's not going to be able to support itself. And instead, the wave is going to collapse entirely, and we call this a wave break. This is what creates the surf, that really turbulent water that's kind of white and foamy right along the beach. If we go into our deeper oceans, it would be a really boring area to try to surf. We need the waves to get tall enough that they break so that we can have surf conditions near the shore in that surf zone.